A typical example of such situation is a pair of this curve and that curve. Moreover, it is easy to see that, as we discussed, it is easy to see that whenever we have a pair of simple closed curve with a unique point of intersection, then first of all, either of them is non-separating. Why? The matter is that if geometric intersection index is 1, then algebraic intersection index is also plus minus 1. We have no possibility. If the geometric intersection index is, for instance, 2, then algebraic intersection index may be 0. But if it is 1, then this unique point may have only one or another orientation, so it is always plus minus 1. So A and B are non-separating, since their homology classes are non-trivial. And algebraic intersection index depends only on homology classes. So, first of all, they are non-separating, and second, if we cut along these two curves, we always get first of all, we get a surface with one boundary component. Second, an easy computation of Euler characteristic says us that we always get a surface of genus G minus 1 with one boundary component. So the situation is unique up to homeomorphism. This is a usual use of so-called change of coordinates principle, that if something is unique up to homeomorphism, that okay, up to action of mapping class group, there is a unique pair of curves with geometric intersection index 1. This is true only for geometric intersection index 1. If we proceed further, then several possibilities exist. But for geometric index 1, there is only one possibility up to a homeomorphism or up to a diffeomorphism of a surface. So we are in this particular situation, and the claim is that the corresponding to then twist satisfy this relation. This is called braid relation. The matter is that if we consider a usual braid group, I'm not going to say a precise definition now. I will do it later when we need it in more details. But now, well, if we have such braid is it consists of several strands that connect points in one. Two collections of points in two parallel planes. So we connect them in such a way, and so that strands are always descending with regarding the corresponding axis, and such pictures form a group under concatenation of braids. And we have such relations where two consecutive strands change in such way, and all others are stable. And well, if this is I and I plus 1 strands with numbers I and I plus 1, then this generator is sigma I, and the standard fact, which is just the third randomizer move, is that these generators satisfy this relation. And actually what we need to know about braid groups is that there exist such relations, and also all relations in this group follow from these relations, and commutation of not neighboring sigma i's. For instance, the braid group on 3 strands, it is just, we have this generator sigma 1, we have generator sigma 2, and this is exactly the group given by these 2 generators and a single relation. Okay, so this is not surprising that this is called braid relation. At the moment I will not discuss how actually this relation can be obtained through some connection with braids, but now we will prove it just directly. It is rather easy. It is just what we need. We need to understand that if we apply these two, this mapping class TA times TB to the curve A, then we get B. Let us check. It is rather easy to check when we try to check some relation between mapping classes. We need to think, we need to do something. But when we just have some relation between that mapping classes applied to some curve give another curve, then we can just check it directly. So suppose that this one is A and this one is B. Let us do this simple computation. If we apply TB, now I would like to draw this curve, to apply the then twist TB to the curve A. So approaching B, we go left. We work with left then twists. So approaching here, we go left, and after that we proceed moving along A. So this one is TB of A. And now we need to, now I just would like to draw it once more. So now I don't want to think about curve B anymore. I just would like to draw TB of A, and actually I am interested in it up to isotopy. Up to isotopy, look, this is the same curve as this one. That one is isotopic to this one, and this is A, and this is TB of A. And now I would like to apply this then twist TA to the curve TB of A. So we go along TB of A, and we go left when we approach A. So we go this direction. And then we proceed here. Well, it is not hard to see that this arc can be pushed here, so we just get this is the same as just this curve B. So we have checked this relation, and now what we know? We know that if some mapping class takes a curve A to a curve B, then if we conjugate the twist along about A with this F, then we get the twist about B. Now we apply this to this particular situation, and we get what we it is better to write here. We get that TA, TB, TA. Now this TA, TB inverse, this conjugate, equals TB. Okay, this is the required relation. We just need to multiply by TA, TB from the right, and we get the required relation. Okay, so we see that if the intersection index, geometric intersection index is 1, then we have this break relation. Well, a natural question is this a unique relation between these two dent twists, or maybe some other relations exist? Of course, there are many relations which follow from this, but does this this relation imply all relations between these two dent twists? And actually, the next interesting question is, and suppose that this intersection intersection number is greater than 1. What are relations between the corresponding dent twists? If the intersection number is 0, then dent twists commute, and we know when we discussed Fenhill-Nielsen coordinates, we discussed that they commute and generate a free abelian group of rank 2 in the mapping class group, provided that A, B are not equal to each other, of course. But if we so we need to consider the cases when this intersection index is 1 and when it is 2. So I now formulate the result. So theorem. Suppose that A and B are isotopy classes of simple closed curves on a surface, on any surface of finite type. So we have surface with several boundary components and punctures. Let us just put X is X and Y, we just denote these two dent twists, so just to simplify notation. And we are interested in the subgroup of the mapping class group generated by these two elements. Then we have two possibilities. First, if the intersection index, geometric intersection index, is greater than 1, is at least 2, then X and Y satisfy no relation. So X and Y generate a free group of the mapping class group, and they are free generators of then X and Y satisfy no relation. That is, they generate a free group with two generators. And second, well, if the intersection number is 1, then at least then we always know this one relation, yes? If intersection index is 1, then actually this is a unique relation between x and y, with some exceptions. I just then the group generated, the subgroup generated by x and y is just x, y up to this relation, so it has such co-presentation. It has such presentation, sorry, for with two exceptions. This is true provided that that our surface is not a torus. Torus is 2, 0, 0. Yes?
Torus 1, 1, 0, 0.
Oh, sorry. Yes. Yes, this is not true on the torus. And this is not true on one punctured torus.
So it means it doesn't, eh?
This is not an SL2Z. This is braid group on 3 strands. Well, and now in these two in the two exceptional cases, yes, if S is torus or 1 puncture torus, then we have an additional relation. Then our group, then the subgroup generated by x and y is, we have two relations, two generators. We have the same braid relations, but additionally we have the following relation: xy to the power 6 is 1. So we indeed have these exceptional cases in yes, and this one is SL2Z. This one is braid group.
Сейчас, а это не центр, это больше, это меньше, в 2 раза меньше, постоянно меньше центр. Центр этой штуки это что? Это будет x, y.
This is well, yes, this should be a center of braid group. XY. Well, XYX is a rotation by 3, so yes, XYX cubed. This is a full rotation of the braid, and this is the. Oh, sorry. Well, let us check it. We have 3 strands. We have X, Y. Well, yes. X and Y. XY is a rotation by we have a rotation by 1/3 of the full rotation. Yes. So yes, xy cube is a center. But here we have. Okay. We'll discuss this later. Let us start with proving the first part. Here, actually, this is a very nice application of the so-called ping-pong lemma, which is a very useful tool for proving that some group is free. This is very useful lemma, and I now would like to formulate it and to prove. Actually, suppose that a group acts on some set. We just need no topology. This is a purely combinatorial situation. So the group G acts on a set X. So this is just a set. And suppose that the following situation holds. We have k elements in the group, and we would like to prove that they generate a free subgroup. We would like to prove that there are no relations between them. Then it is enough to do the following. Suppose that we have found here k subsets, k subspaces, subsets, yes, k subsets. So xi are subsets of x for I from 1 to k. I would like these subsets to be disjoint and non-empty. Non-empty and pairwise disjoint. And assume that the following holds. Now I first write it formally, then I explain. So for any I and j, which are not equal to each other, we would like to have the following property, that if we take the element gi to some power n, which is non-zero, negative or positive, it doesn't matter, just non-zero, and we apply this to xj, then we get into xy, provided that n is non-zero, of course. No. Let it be small n. Yeah. For all. I'm sorry, for all non-zero n.
This is
So the picture is the following: that we have several sets. Yes, we have several disjoint sets. They do not constitute the whole X. They maybe something else is here, but so if we take this one is 1, 2, 3, 4. Yes. If we take G1, then any power of G1, if we apply any non-trivial power of G1, then it maps all these sets to this one, except for itself. Obviously, if G1 maps this element to this one, then G1 to the power -1 maps this to that one. So it is impossible to achieve that x1 is also mapped to itself by powers. but any power of G1 maps all these sets here.
Любая целая, не обязательно положительная.
Yes, any just non-zero power. Of course, zero power maps to itself, but in the same way, any power of G2 maps all these sets here, and so on. Well, as far as I understand, the terminology comes from the situation with two sets. So if you have two sets, then this is some ping-pong game from one to another. If we have several, then the terminology seems somewhat strange, but still. Okay, let us prove this lemma and then apply it to our situation. Proof is rather easy. Okay.
When is that these elements generated?
Oh yes, I didn't formulate. Okay, if we have constructed such, if we are in this situation, then the claim of the lemma is that then G1, Gk are free generators, satisfy no relations, are free generators of a free subgroup. Are free generators of a free subgroup of G. I want to be precise here, since there are possibilities that elements may generate a free group, but maybe not free generators of this group. So I'm sorry for this cumbersome formulation, but this is exactly what you would like to have. Well, they satisfy no relations. They are usual free generators. So this is free group on these particular generators. Okay. Let us prove this lemma. Well, suppose that we have a relation. Then, okay, what is a relation? A relation is a word in our generators G1, Gn, and their inverses, such that this product is equal to 1, but also such that this word is irreducible. What does it mean? That it doesn't contain gi minus 1 and gi minus 1 gi consecutively. Yes? Okay, if it contains the then we can just reduce this word. So we are interested only in irreducible words. So suppose that we have a relation which is some word. Well, I just write something. Some irreducible word in gi plus 1. Irreducible just means that it doesn't contain such subwords. Of course, non-empty word. So we assume that we have a relation, and we would like to come to a contradiction. Okay, if we have such word, then we always can achieve that. We always can obtain another relation which starts from a non-trivial power of G1 and ends by a non-trivial power of G1. Look, why? We have several cases. Okay, if W already starts from G1 to plus or minus 1, and ends by some power of G1, then okay, we already have it. If it neither starts from G1 nor ends with it, if W is of the following form, here we have some GI, here we have some GJ, and I and J are both are not 1. Then we just may add here G1 and here G1 minus 1. Okay, we again get a relation, since this number, yes, a relation means that this number is 1 in G, yes? We again have 1, the word is still unreducible, and we are done. Finally, if we have G1 to some power from one side and not G1 from another side, well, these cases are symmetric, so I may assume that we have G1 to some power plus or minus 1, yes, in the beginning, and it finishes with not G1, with some GI, which is not 1, yes? If we have such word, if the W is of the same, of the following, okay, just we again would like to conjugate it with G1, but the only our wish is that this G1 cannot be, that the word cannot be reduced here. Okay, if it starts with G1, then we add here G1 and G1 minus 1. And if it starts with G1 inverse, then we add G1 inverse here and G1 here.
В любом случае, какой бы ни был случай, можем просто собрать что зелень, которая не в начале, не в конце.
Yes, yes, this is easier, yes, thank you. So we always, now we always achieve that our relation has the following form. It has non-trivial, first non-trivial power of G1 here, then it has some powers of any elements, and finally it has again G1 to some power, well, L. All these powers are non-zero. All these i's consecutive numbers, consecutive indices are distinct, are different. Since otherwise we can unite it. Okay, we have a word of such form. Consecutive indices are different. Now let us consider an element in x1. Oh, no, not in x1. An element in x2. Just take any element. It is non-trivial, so we take any element here. Some element, well, x. Yes? And let us apply this word to that element. First of all, we have non-trivial power of G1. So this non-trivial power of G1 takes this element into x1. Now we have several, next non-trivial power of this. It takes it, so this element takes it to x1, this element. Now we have an element in x1 and we have this non-zero power, so we get into x with number is. Now that and so on. Finally, this element, we again have non-trivial power of x1 here, so we get into x1. So our element takes this x, which lies in x2, to x1. Okay, we have a contradiction. So this element is non-trivial. This is not a relation. So we see that there are no relations in this group, and this is actually a free group. So the lemma is very easy, but very useful. Actually, I would like to maybe this is somewhat not immediately related with mapping class groups, but I would like to start with an example which is maybe one of the first applications of this ping-pong lemma. So, if we just consider the group SL2Z, then we may consider the following two matrices. So when k is a positive integer, and the claim is that these two matrices generate a free group, AK and BK generate, I mean that k is fixed, so we have fixed k and we consider these two matrices generate a free subgroup of SL2Z. In this, provided that k is at least 2.
Если один, то это вот стандартный порождающий.
If it is 1, then yes, then this is not true. Okay. Why? First, this was proved for k equals 2. This was proved by Sanov in 1947, and this is a famous Sanov subgroup of SL2Z. Okay, how to prove this? I would like to prove this since this gives us very nice idea. Almost the same proof can be extended to the case of a mapping class group. Well, the group SL2Z acts naturally on the, okay, it has the most natural action on Z squared, on pairs of integers. So this is just the set of all integer vectors. So let us consider, to get into notation of ping-pong lemma, I denote this by G1 and this by G2. I consider the following subsets. So this will be X. We have this set X on which the group acts, and I consider the following subsets. X1 is the set of all vectors such that the absolute value of A is greater than the absolute value of B, and X2 is vice versa. the set of all such vectors that the absolute value of B is strictly greater than the absolute value of A. Okay, they are non-empty, they are disjoint, and now let us check the condition in ping-pong lemma. So, since we have the situation is symmetric, we just need to prove that a non-trivial power of G1, yes, that a non-trivial power of G1 takes x2 into x1, and the second condition is completely similar. Okay, if AB is in x2, yes, then we have this inequality. The absolute value of B is greater than the absolute value of A. Now suppose that, yes, and n is non-zero. Now suppose that we apply here the nth power of G1. Okay, the nth power of G1 is just a matrix like that. Yes. Now we would like to apply it to our vector. So we get A here and A plus nkb and B here. Okay, if we are interested in the absolute value of A plus nkb, then okay, it is greater than or equal to these two numbers may be of the same sign or of different signs, but so this is just a triangle inequality. But I would like to write module n here since n may be negative as well. So this is since the absolute value of A is smaller than the absolute value of B, this is strictly greater than -1 by. Yes, but here this is at least 1. Since n is non-zero integer and k is at least 2. So we have that. Since we have here at least this inequality is strict, so we indeed get into x1. So just we apply the ping-pong lemma and we get this this claim. Now we would like to do almost the same, but with the mapping class group. So I would like to repeat almost the same. I don't want to erase it to repeat almost the same to see this parallel. So I prefer to erase the the theorem and. Now we have the following situation. We have these two den twists. According to use ping-pong lemma, it is convenient for me to denote them by G1 and G2. We know that the geometric intersection index of A and B is greater than 1, is at least 2. And I would like to do something similar. So for x, we take the set of all isotropy classes of simple closed curves on S. So x is the set of all isotropy classes of simple closed curves. And a natural analysis of these subsets, well, these are just these things are just some kinds of well, A is a scalar product here. A is a scalar product with the first basis vector, and B is the scalar product with the second basis vector. Here, instead of scalar products, we would like to use we would like to use intersection numbers. So I would like to take for x1 the set of all isotropy classes of simple closed curves, such that intersection index of this curve with B is strictly greater than intersection curve of this index with A. And for x2, we would like to take the all simple closed curves such that the intersection number with A is strictly greater than the intersection number with B. Look, my similarity was wrong. We have opposite inequality here. Here the first is greater than the second, and here vice versa. The matter is that this situation should come to that situation in the case of torus. And in the case of a torus, the first coordinate is the intersection index with the second curve, not with the first one. So the correct analogy, correct similarity is like that. Okay, let us check. Okay, of course, the whole mapping class group, and hence these two elements also act on X. So, and these two sets are non-empty and disjoint. One moment. Is it as easy that they are non-empty? Well, disjoint it is obvious, but why they are non-empty?
A and B itself?
Yeah. A belongs to x1, since we have here at least 2 and here 0, and B belongs to x2, so they are definitely non-empty. Well, and now we would like to prove the inequality in ping-pong lemma, the condition in ping-pong lemma. Again, we need to prove only the first inclusion, so we would like to prove that g1 to the power n of x2 gets into x1 provided that n is non-zero, and the second inclusion is completely similar. So let us prove this. Okay, so suppose we initially are in x2. So suppose that C satisfies this inequality. And we would like to apply to this C, look, we would like to apply to this C the nth power of TA. So we would like to apply the nth power of TA to this C, and we would like to compute the intersection number with B of the curve obtained. Okay, and we have estimated this last time, and the estimate which I need today, well, I just like to write down this estimate that we have proved the following thing last time, that this minus module n times this intersection number times that intersection number doesn't exceed I of BC. So last time we have proved this inequality, and now let us do the computation, the estimate. Okay, I would like to say that this number is sufficiently large. So I would like to say that this number is greater than or equal. Okay, since it is not far from here, yes, we may write that it is greater than or equal to modulo n. I write down this one minus I of BC. As in the case of matrices, we use now that this inequality, and we get that this is strictly greater than modulo n times I of AB minus 1 I of AC. So we may replace this I of BC by I of AC, and the value will decrease. But this one is at least 1, since this number is at least 2 and this number is at least 1. So this one is at least 1. And we obtain that this is greater than or equal to I of AC. Well, but note that this is the same as I of the matter is that when we apply the then twist about A to a curve, then the intersection index with A itself doesn't change. So we see that the inequality is strict, since we have here at least one strict inequality, so we get into x1. Well, so this finishes the proof. And we indeed see that the group is free. Okay. Actually, before now we are not ready to prove the second part of the theorem about the case of intersection number 1. So we will return to it somewhat later. But at the moment I would like to concentrate on another question, namely next time we discussed Alexander's method for proving that some mapping class is trivial. Now let us discuss one application of this method. There is the following useful proposition. Well, suppose that a mapping class takes any isotopy class of simple closed curves to itself. So it takes any simple closed curve to a curve isotopic to it. Is it true that this mapping class is trivial? Actually, this is almost true. A correct version of this proposition is as follows: that suppose that a mapping class F takes I would like to write satisfies f of A equals A for any isotopy class of it is better to say homotopy class, since I don't want to consider separately. Otherwise, it would be not true for homotopically trivial curves. So I prefer to say homotopy class for any homotopy class of oriented simple closed curves. Oriented is very crucial here. Then F. Sorry. Sorry. I must say that this proposition is for now. I would like to consider surface maybe with punctures but without boundary components. This is important. I would like to say that F is 1. Actually, if there is a surface with boundary components, then the dent width about any boundary component or about a curve which is isotopic to it acts trivially on isotopy classes of simple closed curves, of course. So I would like to have a curve without boundary components. Well, here it is important that I would like to consider oriented simple closed curves. What does it mean? It means that, okay, if I consider a curve with orientation, then after applying mapping class group, we again get a curve with orientation. These two curves must be homotopic as oriented curves. So the homotopy must regard the orientation. It may happen that well, that some mapping class takes, say, okay, just an important example. We have here a mapping class which is a rotation by pi over horizontal axis. Just called hyperelliptic involution. Just this rotation. Well, it takes this curve to itself, but doesn't regard its orientation. So actually, we will see later that this particular example is a counterexample to this proposition if we forget about the word oriented. In this particular case, when we have a surface of genus 2, this hyperelliptic involution, not only for that particular simple closed curve, but for any simple closed curve, it takes it to an isotopic one, but with opposite orientation.
Если у нас род больше двух, то типа не нужно ориентироваться.
Yes, we'll discuss it somewhat later. So, yes, let us prove this proposition. It's a consequence of Alexander's method, and let us do it. Okay. First, let us consider a surface without punctures. Then I will say which changes should be made for surface with punctures. If we consider a surface without punctures, let us consider the following chain of curves. Actually, chains of curves are a very useful tool for studying mapping class groups. Chain is a sequence of simple closed curves such that consecutive simple closed curves have intersection index number 1 and non-consecutive are disjoint. So here is an example. I would like to consider this particular chain. And I would like to orient these curves as shown in the picture. Okay, now note that this set of curves satisfy conditions in Alexander method. What does it mean? They are pairwise, they are homotopically non-trivial, they are pairwise non-isotopic. Well, we have 2G curves here, let it be gamma 1, gamma 2, and so on, gamma 2G. They are pairwise non-isotopic, and there are we have no triple of these curves such that any two intersect. Odd curves, curves with odd number may intersect only curves with even numbers, so this condition is satisfied. So what we see, if we have a mapping class that takes any of these curves to itself, up to isotopy, yes, any, then our proposition which we have proved last time, I will say that okay, this Alexander method says us that this mapping class can be represented by a homeomorphism which takes all these curves to itself simultaneously. This is what we have proved yesterday, not yesterday, a week ago. So F can be represented by a homeomorphism that takes all these curves such that every curve goes to itself simultaneously. Well, but now we also know, I recall that now we would like, as on the previous lecture, we would like to consider the graph which is the union of these curves. And our homeomorphism may induce some automorphism of this graph. But we know not only that these curves go to itself, but we know that they go with the same orientation. So none of these curves, they are all homological and non-trivial, so it is completely impossible that a curve is isotopic to itself with negative orientation. So if we achieve that these curves are indeed fixed, not up to isotopy, but to truly fixed, then they are fixed as oriented curves. Yes? So this is as oriented curves. But now this means that the corresponding automorphism of this graph is trivial. Since, on every curve consists of two edges. But one of them lies on the right hand side of gamma 1 and the other on the left hand side, I mean in the neighborhood here. So it is completely impossible to change between them. We can distinguish them since near this intersection point, one is on the right hand side of gamma 1, the other on the left hand side. Since the orientation of gamma 1 is preserved, we see that this characterization is also preserved. So we see from here that this phi induces a trivial automorphism, the trivial automorphism of gamma. Hence, we may achieve by an isotopy that this gamma is fixed pointwise. And now look, these curves fill the surface. In the sense that the complement is a disk. By definition, curves fill a surface if their complement is the union of disks and one punctured disks. In this situation, this is just a disk. And so this F is trivial, since we have a unique possibility to extend this trivial homeomorphism on the union of curves to the disk, as we have done last times. Okay. Now I would like I think we should make a break, and after the break we discuss why this condition oriented can be discarded. Almost always, but not always. Okay, let's have a break. Well, let's resume. One moment. Well, we have proved this proposition for before discussing how to get rid of this orientation and when it is possible. I would like to say that this proof can be easily generalized to the case of surface with punctures. If we have several punctures, we can just add here, instead of one gamma 1, we may add several gamma 1s, so that there exists exactly one puncture in any annulus between two consecutive copies of this gamma 1. So we get as many copies of gamma 1 as the number of punctures plus 1. And they are pairwise non-isotopic because they are isotopic without punctures, but once we have these punctures, they are not isotopic anymore. And okay, the same works. There is one exception. If this is a torus, then we should take, if it is a torus, then we have only this gamma 1, and we should take not the number of punctures plus 1, but just the number of punctures. Okay, so that to achieve that. Yes, and any when we delete the whole graph gamma, which now contains several examples of gamma 1, then again these curves fill the surface, since any connected component of a complement, here we have one puncture disks and here we have a disk. So this is not a problem. So the same works. But now what to do with what to do in the case of suppose that I would like to get rid of this oriented, yes, and actually the correct proposition is the following proposition. I just write that the same is true. The same, I mean the same proposition without word oriented. Yes. So if we just delete, provided that with several exceptions. Exceptions are that our surface is not in the following list. The list is I forget to write it down, so I'll try not to forget something. Exceptions are sphere with two punctures, torus, well, S1 which is torus, yes, sphere with torus with one puncture, torus with two punctures, and also closed surface of genus 2. So this is the list of examples of exceptions. For in all other cases, the same is true without any assumptions on orientations. Well, let us prove this and understand why these exceptions appear. First of all, there is a very easy remark, a very easy note. Note that provided if we have these curves like that, then there are only two possibilities. Either our mapping class, well, suppose that we do not know about orientations. Either it preserves the orientations of all these curves, or it reverses the orientations of all these curves. Why? Since consecutive curves have non-trivial algebraic intersection index. The algebraic intersection index must be preserved under any mapping class. So if at least for one of these curves, if the orientation is reversed, then for all others the orientation is already reversed. So and now I would like to add one more curve here. And again, let us start with the case of a closed surface. Let us start with the case of a closed surface with at least 3 punctures. Oh, of genus at least 3, I'm sorry. With at least 3 handles. So we get the same situation. Gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, and so on, gamma to G. The crucial point is that since genus is at least 3, this gamma 4, it would be the most important for me, is not the last one. And we make the following. We add here one more curve, beta, which intersects gamma 4. And once we have this curve, we see that well, again, all these curves fill the surface. They still satisfy conditions in the Alexander method. So all the same is true. But now, look. And again, if the mapping class may either it preserves the orientations of all of them, or it reverses the orientations of all of them. Since again we may consecutive curves have non-trivial algebraic intersection index. But now look, on this gamma 4 we have 3 points: intersection point with gamma 3, intersection point with gamma 5, and intersection point with beta. And if we have achieved, as here, we proceed as here. So we say that by the proposition which was proved last time, our mapping class can be represented by a homeomorphism that fixes setwise every of these curves, all these curves simultaneously. So every of these curves. So it fixes gamma 4 and it fixes each of the curves beta, gamma 3 and gamma 5. Hence, this homeomorphism fixes these 3 intersection points. But now 3 intersection points, unlike 2 intersection points, 3 intersection points provide the orientation of gamma 4. So, well, this gamma 4 was oriented so that the intersection point with gamma 3, the intersection point with gamma 5, and the intersection point with beta goes along this orientation in this particular order. After the mapping class, it should be oriented in the same, since after homeomorphism, the order of 3 points cannot change. So we see that we automatically obtain that our mapping class preserves the orientation of gamma 4 and hence of all other curves, since it preserves algebraic intersection numbers. So we achieve that. So sorry. Oh yes, we have proved this proposition for closed surfaces, except for torus and closed surface of genus 2. What is for the case of a non-closed surface? Again, I don't want to go into all cases here. For instance, if we have at least 3 curves here, yes, so if we have at least 3 points on any curve, then everything is okay. So we need only consider cases when we have less than 3 points on every of curves. So it is not hard to see that in genera 1 and if we have genus 2, then this beta doesn't work, since we have no other curves and we have only 2 points here. But okay, if we have genus 2 and we have the second gamma 1 here, then we have already 3 points on gamma 2 and it is okay. So what are exceptions? Exceptions are, we see that it is these two. These two are exceptions, since for torus with 1 or 2 punctures we have less than 3 points here. Again, if we have at least 3 punctures, then we have 3 points on this curve. This is gamma 2 and these are copies of gamma 1. If we have at least 3 punctures, then we have at 3 copies of gamma 1 and everything works. But actually, in the case of sphere with punctures, we have not yet in the case of sphere with punctures, we need to be more careful. Actually, this method doesn't work at all. I was not careful about it when I proved that proposition. How to deal when we have sphere with punctures. For instance, we may proceed as following. Okay, it is exactly the case, the question of finding a convenient set of curves which fills the surface. Yes? If we have a sphere with punctures, then we can always proceed in the following way. We may consider a curve which a very special case is sphere with 2 punctures. If sphere with less than 2 punctures, then the mapping class group is trivial and it is not interesting at all. Yes? For a sphere with 2 punctures, a good question. What is a mapping class group of a sphere with 2 punctures? Yes, it's z over 2z. If punctures are fixed, then the mapping class is trivial, since we have no, this is the same as for 1 puncture disk. But if we may swap them, and here we see that this curve, this is a collection of curves consisting of 1 curve which fills the surface. And a non-trivial element here takes this curve to itself, but reverses its orientation. So this is an exception. If we have at least 3 punctures, then it is possible to proceed, for instance, in the following way. We take 2 of these punctures, and now for all other punctures we divide them in this way. Yes, I would like to well, this set of curves, so we choose 2 of punctures, we surround them by a curve, and we divide all others in the following way. So this set of curves fills the surface. And if the number of punctures is at least if the number of punctures is at least 5, if it is at least 5, then if the number of punctures is at least 5, then I'm sorry. Yes, then we have more than 2 points on this orange circle, and again the same works without assumptions on orientability. Yes?
Did we use that intersection index algebraic?
Yes, yes. Thank you. I'm trying to cheat a little. We have used algebraic intersection index. Yes. Here it is always 0, so we cannot use it. So yes, if we have at least 5 points, then we have at least 3 points here. So we have more than 2 points on this pink circle. So its orientation must be preserved. But why the orientations of all others must be preserved? We have no reason for that. No reason. The reason from this situation doesn't work. We have no algebraic intersection index. But now look, on one side of pink curve there are 2 punctures, and on the other side there are at least 3 punctures. So these sides can be distinguished. So these points, since there are more than 2 of them on pink circle, they must be fixed. Each of them must be fixed. But now the segment which lies on the side where there are 2 punctures cannot go to the segment which lies on the other side, since these sides are different. So this segment must be preserved, and that segment must be preserved. So the orientation, the 2 points are preserved and 2 segments are preserved, hence the orientations are preserved. So the same argument doesn't work, but here we have another argument. So if it has at least 5 points, then again it is not an exception. We still have this. But okay, let us consider sphere with 3 and with 4 points. Okay, first of all, sphere with 3 punctures. Okay?
But this is sphere with 4 punctures.
Why? No, this is not a puncture. This is just sphere. Yeah, I'm sorry. There is no other way to draw a sphere with 3 punctures. I don't know. Okay. This is a sphere with 3 punctures. Just all punctures are from this side. Okay. What is the mapping class group here? Yes, it's I prefer to denote it by sigma 3 to distinguish from the surface of genus 3. It is the permutation group. Actually, again, if the punctures are fixed, then this is trivial. Well, why? The matter is that well, it's good exercise to think why indeed. I just leave it to you. I don't want to discuss it now, but it's a good exercise to think why if well, the important thing is that if we fix all punctures, then this is just trivial. Yes, it is okay. So we have only up to isotopy, we have only 3 simple closed curves here. Every curve separates this sphere with 3 punctures into 2 components. One of them is a 1 puncture disk and another is a 2 puncture disk. And 1 puncture disk means that any simple closed curves can be there is an isotopy taking it to a neighborhood of a puncture. In a neighborhood of each puncture there is only 1 simple closed curve, so we have only 3 simple closed curves at all. 1, 2, and 3. And if every of these curves is taken to an isotopic to it, then every puncture is fixed, and so we have that the mapping class is trivial. Okay. And the last case is sphere with 4 punctures. Well, actually, a good way to draw it is as follows. Okay, punctures is somewhat like cusps. It's better to draw it as follows. Here we have non-trivial elements of mapping class group. Here we have curves like that separate 2 cusps from another 2 cusps. They are not homotopic to a boundary of a puncture, so they may be non-trivial. Well, here we have the following set of 2 curves which fill the surface. Yes? But, well, actually, in this particular case, no argument. It is not true that either. This is a very exceptional case. In this case, it is possible to change the orientation of one of the curves and not to change it for the other of the curves. Look, there is a rotation about this axis, around this axis, by pi, which takes either of these curves to itself, changes the orientation of one of them and doesn't change the orientation of the other. Neither this argument with intersection numbers nor that argument with count of punctures works. So, and there is another rotation here, which changes these two curves, and well, okay. Actually, to be honest, I forget how to consider this particular case. We may think of it together, or we may just postpone it. Are there any ideas how to finish the proof here? So it would be wonderful to find the third curve, which separates, but this this is invisible. Yes, which separates. We have three possibilities to separate two punctures from another two punctures. But the third curve, if we consider all the three curves, then Alexander method doesn't work anymore, since any two of them intersect. It is not allowed to do this. Well, actually, in fact, this is maybe the last situation when the mapping class group can be described explicitly. Actually, first let us start with let this be A and this be B, and let us start with describing pure mapping class group. That is a mapping class group preserving every puncture. Well, what is this? Yes. Yes, this is a free group just with these generators TA and TB. Actually, we know that TA and TB generate a free group. A good question is why this is the whole group. Yes? This can be proved more or less by hands. The idea is that to take any arc from, say, this point to that point and applying then twists about TA and TB, we may simplify this arc to be like that. It is some idea which can be done. And then the whole group, the whole mapping class group, it contains here pure mapping class group, and the quotient is of course the group of permutations of the punctures. Well, so okay, I still prefer to postpone this one. I suggest you think about this case yourself. Well, and now let us return to to our proposition. Why this proposition is interesting? The matter is that we know that we have proved last time that a mapping class commutes with a den twist if and only if it takes the curve of this den twist to an isotopic to it. So we see that, except for these exceptions, if a mapping class commutes with all den twists, then it is trivial. Since, if it commutes with all den twists, then it takes any simple closed curve to a homotopic one. So, I am not, actually, in fact, it is true that den twists generate the mapping class group. However, we didn't prove this theorem yet. We will prove it soon. But so, in fact, when we say that something commutes with all den twists, then in fact it means that it commutes with all mapping classes. But at the moment we do not know why this is equivalent. So I formulate like that corollary. We have corollary that if a mapping class, an element F in the mapping class group of a surface S without boundary components. It is important. We would like to have a surface with punctures. Commutes with all den twists, with all den twists TA, then F is trivial. Again, provided that we are not in these exceptions. Provided that S is not a sphere with two punctures, a torus, S genus 2, surface a once punctured torus and two punctured torus. Hence, again with the same corollary that of course if F commutes with all elements of mapping class group, then it commutes with all den twists and we get the same. So out of these exceptions, the center of a group is the set of elements which commutes with all elements of the group. Out of these exceptions, the center of the mapping class group of S is trivial. So this is a sometimes useful result. Indeed, in these exceptions, the center is indeed non-trivial. Up to now, we do not know. Okay, for these exceptions, we do not know why this doesn't work. We do not know that our proof doesn't work. But in fact, center is indeed trivial. Actually, the center in each of these cases is Z over 2Z. And it is generated by hyperelliptic involution. So if we have, genus 2 curve we have this hyperelliptic convolution. I mean that the rotation is by the angle pi. Similarly for torus, we have this hyperelliptic convolution. Similarly for once punctured torus. We have rotation about this axis. And similarly for two punctured torus, where the rotation is by angle pi in such situation. So in all these cases there is a hyperelliptic convolution. Yes, two punctured spheres. Sphere is a very non-trivial case. The mapping class group is just z over 2z, and the center is this z over 2z also. So we have to discuss only these exceptions. In each of these exceptions, we immediately see that the center cannot be greater than z over 2z. The matter is that in all these cases, the argument with the algebraic intersection number works. So any element which preserves all isotopic classes of curves either preserves all orientations or reverses all orientations simultaneously. So, okay, so the only possibility for this center is z over 2z. If we have any two non-trivial elements in the center, then their product preserves all orientations, and we get that it is trivial. And in fact, in all these cases, the center is indeed z over 2z, and it is generated by this particular mapping class. Actually, a not easy thing, which I don't want to discuss now, is why these elements indeed in center. Why these particular elements indeed commute with all mapping classes. This is not obvious, and this actually we will see it later when we discuss which elements, which then twists generate the mapping class group. Then this would become obvious. So we just postpone this question, why these particular elements lie in center. But the result is as following, that we have 5 exceptions when the center is z over 2z. In all other cases, the center is trivial. Okay, so in the rest of today's time, I suggest to discuss some other useful relations between den twists. Actually, there are several very useful relations, and up to now we deal with one of them. We have discussed this braid, the only non-trivial relation was this braid relation when the intersection number is 1. The next very important relation is called the lantern relation. Lantern is фонарь по-русски. Вот. Почему фонарь, сейчас чуть попозже объясню. Вот. It looks like that. Suppose that we have a piece of our surface which is homeomorphic to the sphere with 4 boundary components. So this is our surface is here. So disk with 3 deleted disks. So this is a sphere with 4 deleted disks, with 4 disks removed. And here, okay, this is a part of our surface. So the surface contains such subsurface. Okay, here we consider. First of all, let us denote these boundary components by x1, x2, and x3. And second, and x4. Sorry, there are 4 of them. And second, let us consider the following 3 curves. We have 3 curves which surround actually each of these curves has 2 boundary components on one of this each side and 2 on the second. It is we have no reason why we just are interested in these curves up to isotopy. So let it be y1, y2, and y3. So the relation, the lantern relation, is the relation that the product of den twists about these 3 curves, 3 y curves, is equal to the product of 4 den twists about the boundary components. When we are in the mapping class group of a surface with boundary components, then twist about the boundary components, we always mean that we take a curve isotopic to the boundary component. Okay, we consider homeomorphisms that stabilize the boundary components pointwise, so we always consider a curve which is close to the boundary component and isotopic to it. And here we mean the same, but if it's just the actually this relation holds. Initially, it holds in the mapping class group of a sphere with 4 boundary components. But now, okay, if this sphere of 4 boundary components is embedded into any other surface, then of course there is a homomorphism of mapping class groups, and since this relation holds here, it also holds here. So whenever we have such configuration of 7 curves on our surface, we have this lantern relation. Okay, and well, why it is a lantern relation? The matter is that these 7 curves, the same configuration can be drawn in another way. We may put it x1 here, x2 here, x4 here, and x3 here, and the curves are like that. This one is y1, this one is y3, and this one is y2. It is not hard to see that this is indeed the same configuration of curves, just we deform this into this. The idea why it is true. The idea is that this looks like some lantern. I don't know why, but the idea was like that. Okay, why this? The relation is very useful. Actually, often the first non-trivial case is when we have. If we have intersection index 1, this is more or less trivial. This is something easy. But the first non-trivial case is when we have geometric intersection index 2 and algebraic intersection index 0. And here we just have this. And it is very useful that obviously these four dent widths, they commute to each other. So it is actually very useful that we can replace some difficult dent widths that do not commute by dent widths which commute. How to prove relations like that? First, note that it is sufficient to prove this relation is in this particular situation, when our surface is this sphere with 4 disks removed. So we may consider this particular situation. In this particular situation, we may apply Alexander's method again. But since the surface is with boundary, we need to apply it in modified form when we consider not only simple closed curves but also simple closed arcs connecting boundary components. Namely, let us find here 3 simple closed arcs which the union of which fills the surface. It is not hard, it is actually okay, let us consider these 3 ones, and I consider three arcs. This one, that one, and those one. These 3 arcs they are simple arcs with endpoints on the boundary. Boundary is pointwise fixed. So, and the union, the complement is a disk. So we are, and they are pairwise non-intersection. So as for curves, if we have a mapping class which preserves all these 3 arcs up to isotopy, then it can be represented by a homeomorphism that preserves all these 3 arcs pointwise. And hence it is trivial in the mapping class group. So to prove that, we would like to prove that the element, that this product with this i's to minus, we would like to prove that this element is trivial. Yes? So it is sufficient to prove that it preserves all these arcs up to isotopy. And hence it is sufficient to prove that this element F1 and this element F2 change these 3 arcs in the same way. So now let us just draw a picture. So first of all, let us try to apply here the element on the right hand side. It is easier since the then twists are about curves which are disjoint. So look, this orange arc behaves as following. For this orange arc, these two then twists are not important. They do not act on this arc. But here, when we approach, we go left. So this orange arc behaves like that. Note that this boundary component is preserved pointwise, so we cannot make an isotopy going back. But here we again go left. Left is this direction. So we obtain a picture like that. And similarly for two others. Oh, which of them? This one is go left. Oh, sorry. This is right. This is not left. I'm sorry. Left means here. Yes. And here we have the same. Okay, and the third one is left. Well, we get a picture like that. Well, now we need to apply these three then twists to the same three curves. Let us do it step by step. First, I would like to apply the then twist about y3. Y3 is here. So first of all, it is obviously that this pink curve doesn't change. Oops. So this pink, it's not, it is better to draw them more close to the center. This pink doesn't change. And y3 is here. So for red one, when we approach here, we make a full turn like that. And for this green one, when we approach here, we go left and make a turn like that. Okay. This is after y3. Next is y2. Y2 is here. Yes? So when we apply y2, the green curve doesn't change. Oh, no, it changes, sorry, no, not. Yes. So let us. Well, okay, let us try to write it down. First of all, for this pink one, we approach here and we go left. Okay? Actually, I don't want to, if I try to draw them all here, yes, it is, I need only to prove it for each of the three curves, so it is better to deal with them separately. This pink one is the easiest situation. Okay, this is after T1, Ty2, yes, and when we apply Ty1, we get, okay, where is y1? Y1 is here. So instead of, when we approach here, we must go left and instead go like that. Yes? So we just yes. No. We approach here, we go like that and then go from this side. Okay? This is exactly what is required. Well, exercise. Draw the same pictures for the two other curves. Unfortunately, we cannot say that, okay, because of symmetry, it's the same. We have no symmetry before we have proved this. So really, the useful corollary is that, in fact, this Ty1, Ty2, Ty3, it is equals to Ty2, Ty3, Ty1. So it doesn't change if we make cyclic permutations. But this corollary is only after we have proved this proposition. So unfortunately we haven't this symmetry. This lantern relation initially is not so symmetric. Yes. If we permute two y's, then the same is not true since right turns to left. So for right twists, the same is true with minus ones, but it is not a new relation. Just if we take this particular relation and takes the inverses of two parts, then we get Ty3 minus 1. Okay, this is immediately takes is Ty3 minus 1, Ty2 minus 1, Ty minus 1 equals to the. Here the order is unimportant since they commute. Well, actually, this lantern relation is useful in many situations, but the first situation when it is rather pretty is to prove that the abelianization of the okay, for each group we have the abelianization. We can consider the quotient of this group by the
Commutators?
Yeah, by the commutator subgroup, I'm sorry. And here this lantern relation actually allows to prove that the abelianization of the mapping class group is trivial, starting from genus 3. But okay, but in fact it would be an honest result only after we understand that then twists about non-separating curves generate the mapping class group. But we will prove this soon, and I think it's a good time, though we haven't proved it yet, I think this is a good time now to discuss why this relation affects how it allows us to deal with abelianization. So the idea is as follows, that if genus is at least 3, then we may in our surface we may find a subsurface homeomorphic to the sphere with 4 boundary components, so that all these 7 curves are non-separating. So I would like to embed this surface with 4 components into the surface of genus 3, so that all these 7 curves, 4 x's and 3 y's, are non-separating. Okay, let us do something like that. Well.
Наверное, соединить соседние между ними трубочку.
Yes. This is the surface of genus 2. At the moment it is the surface of genus 2. But here, okay, look, x's are non-separating. Y's
Y3 is separated.
yes, y3 is separating, but y1 and y2 are non-separating. Okay? Now I would like to add here one more handle. So I just take a small tube and connect these two. Okay, and now all these 7 curves are non-separating. Yes, each of them is non-separating. But okay, if we already know, I have said that this is a result modular the theorem that the mapping class group is generated by twists about non-separating curves. Yes? But look, any 2 twists about non-separating simple closed curves are conjugate. Indeed, we know that for any 2 non-separating simple closed curves, there is a homeomorphism which takes one of them to another. So if we have 2, if A and B are 2 non-separating simple closed curves, then TA is conjugate to TB in the mapping class group. Since there is a homeomorphism that takes one of the curves to another. But hence, in abelianization, they are equal to each other. Yes? So in fact, the fact that abelianization is a cyclic group is immediate from the fact that the mapping class group is generated by twists about non-separating simple closed curves. Since all these generators go to the same generator, to the same element of abelianization. Yes? But, okay, now look on this relation. We have 3 then twists about non-separating simple closed curves, and here we have 4 then twists about non-separating closed curves. When we go to abelianization, we see that all these elements become the same. So this element cubed and its 4th power are equal to each other. Hence, this element is trivial. So we see that when we prove that the mapping class group is generated by twists about simple closed curve, we immediately obtain that the center is trivial. Actually, for genus 2 and for genus 1, the centers are not trivial, and we'll see it later. Okay. Now, several other useful relations. Maybe I do not have enough time to prove them. I just now formulated them. And maybe it is a good exercise to prove them by means of Alexander's method. All these relations can be proved by Alexander's method. Actually, maybe this is not a good theorem, this is such meta theorem. Any correct relation can be proved by Alexander's method. If you are given, Alexander's method doesn't say how to predict relations, how to find them. But if somebody gives you a relation and says this is a relation in the mapping class group, and you need to check it, that any reasonable relation can be checked by means of Alexander method for some set of curves. Okay, so there are two more important relations, and these relations are related again to chains of simple closed curves. So first consider the following situation. Suppose that you have a chain of 2G plus 1 curves. Now suppose that our surface is closed and we have such chain of 2G plus 1 curves. Actually, it is not hard to see that any chain up to homeomorphism is like that. So let it be. Okay, it's usual. Since it's chain, it's usual denoted by C. Okay. Now, the fact is the following: that let us consider the product of all these den twists in some order, say from that, and then the product in the opposite order. So consider the element like that. Okay, we may consider such mapping class. The fact is that this is the hyperelliptic involution. The hyperelliptic involution can be written as the product of den twists in this particular way. Okay, and at the moment it is not yet the relation between den twists, since here we have hyperelliptic involution. But okay, let this element be f. Yes. Oh, sorry. It is I. Iota. I do not need another notation. But okay, we know that iota squared is 1, and iota commutes with any of these den twists, since the hyperelliptic involution takes every curve in this chain to itself. So we have some number of relations. Putting this here, we get such relations. Okay, there is a funny consequence. Look, if we write down that iota squared is 1, yes, then this is a relation which contains only left den twists. It doesn't contain inverses of them. Yes? We get this times again this times this equals 1. But now let us take one of them, say this last one, yes, and put it on the right hand side of this relation. So we get that TCG plus 1 inverse is a product of left den twists. Of left den twists. So when we will prove that den twists generate the mapping class group, we in fact immediately obtain the following consequence, that any element can be written as a product of only left den twists without inverses. So somewhat, I do not know exactly when this is useful, but it is interesting, maybe. Okay, and another relation is in a similar situation, but when we have a shorter chain, not the chain such maximal chain of 2g plus 1, but sometimes we have shorter chain of k and of k curves, and here we have there are two important cases. First of all, suppose that we have, so this is C1, C2, C3, and so on. Suppose that this chain is consists of even number of curves. Let us cut along all these curves. What we get? It is easy to see that we get one component, a surface with one component of the boundary. It is just easy to see that all shears, all sides of this, we can pass through these cuts from any point to any other point. So we have one boundary components. And this means that, okay, actually this boundary component, if we go near it, okay, in some regular neighborhood. Up to isotropy, this is it is this curve. So let it be D. Up to isotropy, we get this particular curve. And another situation is when we have an odd number of curves. When we have an odd number of curves in the chain, then it is easy to see that when we cut, we get two connected components of the boundary. Well, the easiest situation when we cut along one of them, we get two connected components, yes? And similar, and actually these are exactly these two connected components up to isotropy. So we have the following relations called chain relations. Let it be C1 CK, but in here also C1 CK, but here K is even and here K is odd. So in the first situation, when K is even, if K is even, then we have the following. First of all, if we take the product of all these den twists from TC1 to TCK, and we take this element to the power 2k plus 2, then this is the twist about the boundary curve, this separation curve. Okay. Second, actually there is another funny relation. Let us take the product, the square of the first then twist, and then not squares, then just usual twists. If we take this to the power 2k, then we again get the twist about the separating curve D. Well, in this situation we have D1 and D2, two curves here, and for k odd, we again have two forms of this relation. First of all, if we have TC1, TCK, in this situation we need to take the power k plus 1. Then this is TD1, TD2. And similarly, we can take the square of the first one, and then like that, to the power k. This is exactly, again, TD1, TD2. Well, unlike previous relations, here the proof of it by Alexander's method is not very easy. For that one, it is not difficult. We just need to... okay, I think it is obvious here which set of curves to take, yes? To apply Alexander's method, these curves fill the surface, and it is... here it is also here it is not so easy, and here it's because of these powers it is somewhat cumbersome. Maybe not next time, but soon I will explain how to obtain these relations, not from Alexander method, how to obtain them from some conceptual. Oh, sorry, I need to finish. Just one word. That look here. If we see here that the then twist about curve D has a root. We have element whose power, non-trivial power, is a then twist. Here this curve is separated. Actually, from these relations, next time I will show this, it is not hard to show that then twists of non-separating curves also have some roots. In fact, on surface of genus G, then twists have roots of order 2G+1. So all then twists about non-separating curves are conjugate to each other, and they generate the group. But surprisingly, each of them is 2G plus first power of some element. So there are generators, but these generators are all powers. So such. Oh, sorry. It's a misprint to G minus 1, of course. Yes. Yes. Thank you. That's enough.